Good evening, good morning. Welcome to this IPA IOP web series.
So, we extend a very warm welcome to the panelists, speakers, and other dignitaries present here, and also welcome all the participants on Zoom and on YouTube for this IPA IOP Cockroft Walton webinar 2022. This two-day event is conducted jointly by the Indian Physics Association, popularly known as IPA, the Indian Physics Association, and the Institute of Physics of UK, commonly referred to as IOP. I am Madhurima, a professor of physics at the Central University of Tamil Nadu, India, and the convener of this program. I now invite Vandana Nanam, General Secretary IPA and a senior professor at IIFR, to briefly introduce the webinar and chair the session. Vandana, over.
Thank you, Madhurima. I hope everybody can hear me well. A very warm welcome from IPA to all of you. The Indian Physics Association, or IPA, was founded in 1970 and has more than 4,000 members spread all over India. IPA aims to help the advancement, dissemination, and application of knowledge of physics and promote active interaction within the community. IPA has been an active platform for physics community in India for last 50 years and has facilitated interactions through many different channels. IPA also works for promoting gender equity in physics, liaises with national and international bodies, and today's program is one such example. Today's program is brought to you in collaboration with Institute of Physics UK, which is the professional body and learned society for physics in the UK and Ireland, inspiring people to develop their knowledge, understanding, and enjoyment of physics. IOP is also a world-leading science publisher, and today's this lecture series, the exchange, was set up in 1998 by IPA and IOP as a bilateral exchange programs between UK and in India. In alternate years, the speakers, the eminent scientists from India and UK visit the partner countries. In India, these lectures are known as Cockroft Walton lectures, while in the UK, they are known as Homi Bhabha lectures. Last 2 years, because of the pandemic, of course, this program was hampered, and we have had this thing instead of in person, in online version of it. In 2020, the online lectures were organized in India, and in 2021, they were organized in UK. This year in 2022, although the travel was opening up, it was thought that timely to use the opportunity of online platform and have a webinar on a topic which has become close to everyone's heart, and as COVID-19, the lessons for the future. In India, these lectures are supported through a grant by Department of Atomic Energy and Tata Trust. And today, we, as a part of this webinar, therefore, is thought of as a 2-day event. Today, we will have 2 lectures, and tomorrow there will be a panel discussion on this aspect. So let me, without much further ado, let me begin with today's first lecture. Today's first lecture will be given by Katerina Kauri. I hope I have pronounced the name correctly. She is a senior lecturer in applied mathematics at Cardiff University, UK. She holds the Doctorate in Philosophy from Oxford University and BA in Mathematics from Cambridge University. In her research, she tackles cutting-edge interdisciplinary challenges in physics, biology, engineering, business, and society. During the COVID-19 pandemic, Katerina has been working intensively on models of COVID-19 transmission in collaboration with the University of Oxford, advising the Welsh government. She has won several research grants, including a Tackling COVID-19 grant from the Welsh government. She is passionate about science communication and public engagement. She has been a TEDx speaker and TED educator. She's currently the Director for Impact and Engagement at Cardiff Mathematics. She has coordinated 2 European study groups with industry workshops where the teams of researchers solve real-life challenges using modeling and data analytics. She is particularly interested in how science and policy making can come together efficiently. She has also been the Vice President of the Parallel Parliament for Research, Innovation, and Digital Governance in her home country, Cyprus. In 2021, she was nominated as Woman of the Year in Innovation, Cyprus. We are very fortunate to have Catherine today to tell us about modeling airborne transmission of viruses. Over to you, Catherine.
So it is with a great pleasure that I am participating in the Cockroft Walton lectures this year. Thank you very much, Professor. Thank you, the Indian Physics Association and the Institute of Physics in the UK for the invitation. It would have been great to visit India, but as you said, the pandemic is still on and the traveling is difficult. And as you mentioned, I'm going to talk about COVID-19 and describe the work I have been doing over the pandemic with collaborators at the University of Oxford and in collaboration with the Welsh government. So without further ado, I'm going to talk about airborne transmission of viruses. And the outline of my talk is an introduction to airborne transmission. Then I'm going to explain how we have developed a quick-to-run model to determine the infection risk in a room. I'm going to pose a question whether air purifiers can make rooms safer. Very briefly, I'm going to talk about some other work we have done with another team of people on interventions in classrooms. And I'm going to finish with my conclusions and some open challenges. So you might all remember at the beginning of the pandemic what we did. We were all very scared and we have been told repeatedly we should wash our hands all the time. Eventually, the mask wearing came into place and we should keep our distance from our fellow people 2 meters usually. So this is the campaign that ran in the UK, hands, face, space. Lots of antiseptic. A woman on Twitter had put her chocolates, a photo of her chocolates in soap. I was also myself washing my groceries, I must say. So, however, a story started manifesting very early on, and it took some time to fully come into place. So what happened in a restaurant in China in January 2020, 7 to 9 people were infected by just one person in about 1 hour. And this could not have happened with people touching surfaces. It was done because of the contaminated air that was recirculated by the air conditioning unit. And then in March 2020 in the US, there was a choir practice. And after that practice, 52 people were infected, and in fact, 2 unfortunately died. And again, this could not have been done by touching people. It has to do something with the air. And in Germany, in June 2020, staggering numbers, 1,500 people in a meat plant were infected due to circulating air. So when the plant was closed, then these kind of incidents with the meat plants were blamed for the spike in the cases in Germany and other places in Europe, in fact. So as scientists always do, they were gathering this evidence was coming out. So by July 2020, many scientists understood that SARS-CoV-2 is transmitted through air. And there was a very highly cited paper by famous population health scientist Lydia Morawska And then there was a letter that 239 scientists from 32 countries wrote. It was an open letter and was urging the World Health Organization to re-examine airborne transmission of COVID-19 and adjust the recommendations. And this is from India as well. So it was all over the news, all over the world. Please do something, change the guidelines. So what is going on? What is airborne transmission? So you can see here a woman sneezing, and you can see a cloud, but the cloud differs, right? Because you have these large droplets, you can see them falling to the ground. And this is what gives us the 2-meter social distancing guidelines. However, you have aerosols, these are smaller particles, and they move like a cloud, a bit like how the smoke from a cigarette would spread around in a room. And in this way, they go and infect people much further than 2 meters sometimes. So what are the physics of airborne transmission? You can see here a schematic from Lydia Morawska's paper when she was talking about that we have to face the reality of airborne transmission. The large droplets fall to the ground within 2 meters. The small droplets, they reach the other person, they can infect the other person. And the physics are the following. So you have this cloud of small droplets, they are spreading or diffuse, as we say. They are transported by the flow in the room, and that we call advection. They settle due to gravity because however small they are, they have some mass. They quickly evaporate. And then also another discussion we had with many virologists when we were working with the government is that the virus also deactivates. They didn't know how many hours it takes for the virus to deactivate, but now it's a certain scientific fact that it deactivates. And then if the susceptible people get enough of those particles in their body, they may get infected. This will depend on somebody's immune system. So takeaway message, small particles, aerosols containing the virus can float in a room and infect for hours. And this is obviously very dangerous, and we have seen these stories from around the world. So how can we model airborne transmission? So one option we have is computational fluid dynamics, or CFD models. These models accurately simulate the complex airflow and particle transport in a room, but simulations are expensive and time-consuming. It can take days to months to run. And the information it generated is only about one setup. If you change in that picture there, which is from the University of Colorado and appeared in, Oregon, and appeared in BBC News, if you change the location of one table, you have to rerun the CFD simulation, and then again might take weeks or months. So at the other end of the spectrum, there are these very simple models that came from earlier epidemics, the Wells-Riley models. And the virus spreads uniformly, and the location does not matter in the room. So you lose a lot of information. You don't know anything about the geometry of the room. One thing you know is that some particles are coming out of somebody's mouth when they are infected. And then there are 3 mechanisms that these particles can be removed from the room. One mechanism is ventilation, and this is quantified by the air changes per hour, how frequently the air is refreshed in the room. You have biological deactivation, which I mentioned in the past, how quickly the virus stops being active. And you also have gravitational settling, and this is very quick to run, and this is why it has been used extensively during the pandemic to also inform policy making. And you can see here 4 papers from the pandemic written during the pandemic that use this model. But the model is not accurate for many real cases because the location where you are in the room does not matter. So can we develop a model that gives the best of both worlds? We want a model that can predict the change in infection risk in the room and is also quick to run, unlike the CFD models. So we did some CFD simulations, and you can see here complicated looking airflow in the room. And you can see here that the air recirculates. And this inspired us to put down this recirculating loop, as we call it, recirculating flow, and we flatten that in 2D. You can do that mathematically. And this allowed us to extend this very simple Wells-Riley model to a model that includes advection, diffusion, and reaction, the NDR model, as we call it. And this model has 3 additional terms in the equation. You don't need to understand the equation if you don't like equations, but these terms are the ones that provide us with information about the concentration and how it changes in the room. It's not everywhere the same. And we had various modeling assumptions. Always when you're doing modeling, you have to do these assumptions, and they let you get some insights, and then you might go back and change the assumptions. So the assumptions we use here is that there is a constant emission rate of viral particles. The particles are coming out of somebody's mouth are all the same. They have the same size. They contain the same amount of virus, and they are also emitted with 0 velocity. By doing that, we are restricting attention to breathing and talking. And why we did that? Because it's also simpler to handle mathematically, but it's also the worst case you can have, because if you have coughing and sneezing, you are generating more virus in the room. So when to see, even in the cases that you think you don't generate much, is it still danger? And the answer is there is. I'm spoiling the suspense for you. So the other thing we assumed is that the particles are transported by the airflow with constant velocity. And we also encapsulate all this complexity of the flow that you have seen in the CFD simulations into a single diffusion coefficient K. You can see there in the second green box. And we have published this in the Proceedings of Royal Society A, and you can see more information there. The sync term, as we call it, the 3 processes of removing the particles are still the same as the Wells-Riley model. This admits a semi-analytical solution, as we say in mathematics, and is very fast to run. So we can do that. I'm gonna not bore you with the details. The important thing to remember from here is that you can get from, again, a literature that arose during the pandemic, information about the number of particles you emit when you are breathing versus when you are talking. And you might want to remember that you emit 10 times more particles when you are talking. So one early recommendation we did to the government when we realized that is that you should talk less in crowded places. Of course, this can be counterintuitive when you have to talk like in a classroom where you want things to be interactive and educational. And also we assumed the mask that it reduces this emission rate by 50%. And we got, again, information from the pandemic literature about the biological deactivation and the gravitational settling rate. We also adapted Wells-Riley formula for the infection risk. This is how probable it is to be infected. And you can see this will change with X and Y. That means where you are in the room, your location in the room. And one other assumption we have made is that all susceptible people need the same dose amount of virus to be infected. And this is a simplification again, because we know very well by now that the immune system of somebody, their age, etc., are very important in deciding whether they are gonna be infected or not. So coming back to the restaurant super spreader event, let's look at this in a bit more detail. You have this person A1, that was the infectious person, is sitting in table A. And we simulated over the whole restaurant, but the area of interest is that zone of recirculation where the 7 to 9 people were infected. And we used our model, we solved our model, and we predicted that the infected people are 8 out of 20. You can see that in the right plot where you have 40% here to be the average infection risk. And this agrees with the actual number of 7 to 9 people out of the 20, and that's a very good agreement. Our model also agreed with other CFD simulations. This was a very well studied case with about 2 or 3 CFD simulations coming out. So the other thing we looked at is a courtroom super spreader event in Switzerland in October 2020. There you have the infectious person being P1. In this case, P1 was mostly silent, and the ventilation broke down in this room, and there was a court hearing for about 3 hours. And this person, even though they were mostly silent, they managed to infect 4 to 5 people. And we went and calculated the dose that these people have received, and we calculated the infection risk, as you can see here in this table. And I want to draw your attention between P5 and P10. P5 was infected, P10 was not infected. So you can see they are almost the same distance from P1, the infectious person. But the reason that this is the case and the dose for P10 is much lower is because they have stayed in the room much less. So this is a reminder that it's not just the location, it's also the time spent in the room that matters, whether you're going to be infected or not. And in fact, this is something we know and we've heard many times, but this is a quantification of this phenomenon. So, okay, why do we model? Why do we model airborne transmission? Well, the reason is because we want to understand this so that we are able to reduce it, right? And one primary way of reducing airborne transmission is to improve the quality of the air, is to improve ventilation. And there are various types of ventilations, mainly split into natural ventilation, that is when you're opening your doors or windows, and mechanical ventilation that comes from air conditioning units and mostly that. And then you see here on the right is a picture that brings us back to the past during the influenza pandemic, the beginning of the 20th century. You see here an emergency hospital outdoors because they understood even back then that the virus can be less transmissible in the outdoors. So, and the UK government adjusted their campaign, and you see now hands, face, space, and fresh air. And they encouraged us to see our friends outdoors. People spend months and months not seeing their friends, not seeing family. So they meet, but meet outdoors. And this is because the air changes per hour there are much, much higher than when you are indoors. And we want to go away and calculate the effect of improving ventilation and quantify that as we do as quantitative scientists. So we looked at 4 ventilation levels, very poor ventilation. This is just 0.12 air changes per hour. We looked at poor ventilation. This is 6 times more, 0.72 air changes per hour. And then we looked at the ventilation setting recommended by the Association of Heating, Refrigerating, and Air Conditioning Engineers, ASHRAE in brevity. And this is 3 air changes per hour. And during the pandemic, ASHRAE revised their recommendations and they doubled the number of air changes per hour you need to have a well-ventilated environment. But this is, I must say, a hard to achieve number in many, many indoor spaces. And I have to say that poor and very poor ventilation values were taken from classroom data from a study that was done before the pandemic in 2008. And there is a reason for that, because we wanted to understand transmission and ventilation effect in classrooms, also motivated by our collaboration with the Welsh government. So we looked at the average size classroom. And we, you can see here, infectious person in the center of the room, constant velocity 0.15 meters per second. This is the typical velocity for an air conditioning unit. And then we solved our model very quickly, as I said, in seconds, and we get the aerosol concentration. And we see that very significantly in the room. So you can see here in the left plot, when we have poor ventilation, that when I go very close to the infectious person, I have 28 R, and I go a bit further away, 2 meters is 16 R. And then if I move across to the picture on the right, where I have 4 times more ventilation, I see that the concentration is about halved. And remember, I told you that you emit 10 times more particles on average when you are talking instead of breathing. So the way we've done our model is very good because you have this parameter R and you can take any value you want, breathing or talking or with a mask, in fact. So then the other thing we wanted to calculate is the infection risk, and we did that as well. So you see one infected person now that we decided that they are breathing at the room center, and after 1 hour, you can again see that if you increase ventilation 4 times, the infection risk is halved. And also you have to remember, as I also mentioned before, time matters. So infection risk increases with time. And here you also see the 4 different ventilation settings we have considered. So the other question I promised to tell you something about is whether we can increase ventilation in other ways. And one such great way to do that is air purifiers or air cleaning devices. So the HEPA filter air purifiers can reduce COVID-19 transmission. It was a frenzy of research activity during the pandemic where people were studying these devices, and they have shown that they can improve things. So what we have done, we have incorporated air purifiers into our quick to run NDR model. And this study was led by Dr. Alexander Preedy, and brilliant postdoc we had at Cardiff and co-supervised by Oxford. And then we also did some CFT simulations with 2 other brilliant postdoctoral researchers, Dr. Aaron English and Dr. Attila Kovacs. And Attila still works actively on this topic currently with funding from Oxford University. So what is the air purifier? Is a fan and a filter, and you have air going in and air going out. So you hope that the air goes out is completely clean. Of course, this will depend on the proportion of particles trapped by a filter. We call this eta with a symbol. And also the Q is what characterizes the fan, which gives you the volume of air passing through the fan per unit time. And this defines the efficiency of the air purifier into a single number, which we call clean air delivery rate, or abbreviated CADR. So as I said, we included this into our model, and we put an inlet in the upper layer, an outlet in the lower layer of our recirculating setup. And you can see here that for a weak purifier that is 100 cubic meters per hour, the CADR, there is very mild change in the flow field in the room. But a strong purifier, 10 times stronger, you can see a quite significant change in the flow field. And this, of course, you expect that it will also affect the concentration in the room. So this is what Zander simulated here. Purifier off, weak purifier, you see about half of the concentration, and then a drastic reduction with the strong purifier, which is 10 times stronger. And one important takeaway message from here is that we have shown that you can convert a poorly ventilated room to a well-ventilated room using a strong purifier. So you can see here that I have background poor ventilation in a room. So I may not have any air conditioning, I may have my windows closed, etc. But then I put in a strong purifier of 1000 CNDR, and then it brings me to the ASHRAE post-pandemic ventilation, which I said is a difficult thing to achieve. So I would like to thank now my collaborators, Professor Ian Griffiths at the University of Oxford, with whom we wrote together a grant to the Welsh Government, the Tackling COVID-19 grant. This allowed Aaron English, Zander Preedy, Raquel to be employed at Cardiff University and work on these challenges. And we also had Zakaria Lau working in Cardiff and in Oxford. And as I said, Attila is still working on air purifiers with me and Ian. And we'd like to acknowledge funding from the Welsh Government, the Royal Society, through the University Research Fellowship of Ian. Cardiff University also supplied funds, and we also worked for a brief time with Smart Separations Limited that wanted to launch a small portable air purifier for restaurants and classrooms. And we advised the government, as we said, this meant we did policy briefs for the government that on air purifiers, on perspex screens, etc. We designed a web app. You can go and see that on Oxford at the moment, and we are working on doing a Polish version now. And finally, this is my final thing I want to say, working with another sub-team in Cardiff University and Josh Moore and Dr. Thomas Woolley, very close collaborator, and Professor Dale, we also incorporated airborne transmission modeling into a flowchart they have created in deciding mitigations in classrooms. And we have found that it's better to improve ventilation than do very frequent testing, because you remember that people were thinking, oh, should we test the students? Should they isolate the students? So all this flowchart can decide that for you, and you can find again an app that you can play with, and I put the link there. So summary and open challenges. We developed a new model for airborne transmission of viruses that quickly gives how the infection is varies in a room as time goes by. We can very easily change ventilation, activity time, breathing, talking, mask without mask, infectious dose, the room size, the personal location, and we can rerun in seconds, very important in a fast evolving pandemic. And some open challenges. What happens when you incorporate different particle sizes is what Raquel was working on for some time. Infectious people that are moving and not stationary as we consider them. What if you have furniture? And again, comparing mitigations, max of different efficiency, air purifiers, air conditioning, windows, what to do. So thank you very much for your attention, and very eager to take your questions.
Thank you, Katerina, for a very nice introduction to this new model and bringing out all salient features of it. The audience has already typed in a few questions. So we'll first start with the questions from Zoom webinar. I would also further announce once more that all the attendees, please type your questions either in Q&A or chat box. And we will also see if there are questions in the YouTube. We have a few audience there. So I can read out the question for you if you want, or you can see the Q&A box.
Yeah, I'm hearing Alan Calvert's question. Is that correct? That's the right place, right? Yes. Okay. Correct. So should I read it out in case other people cannot see?
Yes, please. Yeah.
Yeah. So following the Chinese choir incident, brass bands were first prevented from rehearsing, then required to cover the instrument bells with a filter. I play the tuba, oh, that's nice, with a bell diameter of about 50 centimeters and otherwise exhale through my 0.5 cm nostrils. By my calculation, any particles that manage to travel through 5 meters of brass tubing will be expelled at 0.001 of the velocity of normal breath. Did the band or filter cap make sense? This is a very nice question, but unfortunately, as you did, Alan, we have to do the calculations. Feel free to contact me and we can see, we can discuss this further. But it's about putting down the geometry of what you are describing and thinking about the initial velocity of the particles, as you did, as I understand, and deciding the distances particles have to travel. So it's not something I can answer now, I'm afraid. But a very interesting question, nevertheless. Should I go to the next one?
Yes, please.
So this is from Mr. Arnab Bhattacharya. Sorry for pronouncing things not correctly. That's the case. So the recirculating flow loop allowing you to convert the 3D problem to 2D seems to work for a room with an air conditioning system with input at the top. I'm guessing from the figure, and recirculation which looks symmetric. How easy is this to do with a room with windows and no forced circulations, apart from maybe ceiling fans? Okay, so we thought a bit about introducing windows, and as I said, it's one of the open challenges. So basically, the way we will do that in our model, we have to modify the boundary conditions, and this will change the easiness with which we run the simulation. We will need probably a tool like console multiphysics. It should still be fine because we can still use the assumptions of the NDR model we use, but we need to change the boundary conditions, and then we'll lose the semi-analytical solution we had due to the symmetry that you have correctly identified. I'm not sure, because, you know, when we are teaching or discussing with people, we can see the response, but I don't know now whether that's satisfactory. But yeah, it can be done, but it will make the simulation a little bit more complicated. I think that's the summary of my answer. And then the same person, let me answer a question from another person, because I'm going back to Mr. Arnab's questions. So from Liz Parvin. Thank you for an interesting talk. Can you tell us what effect Perspex screens have? Are they worth having in shops, etc.? So that's a very interesting question. So basically, the other thing we had seen relatively early in the pandemic is that these Perspex screens went up everywhere, right? And you still have them in the UK. They are in many, many places. You can go to the doctor and you see people talking to you behind that plastic screen. The thing is, because again, we're coming back to the virus being transmitted by air. Imagine that you smoke a cigarette in front of that screen. Wouldn't the smoke of the cigarette come to you from the sides? It would. So it's not really that effective in many cases. We also looked particularly in Perspex screens for taxis. And if I remember correctly, that's been more than a year ago. You create basically areas where the virus is more focused. So for example, if you split the car in two, the taxi in two, you might end up protecting the driver, and that's a good thing. But then you have two passengers and they are in a smaller enclosed space, which is half the taxi, then they will have a higher risk of getting infected. So it's not an easy answer whether Perspex screens are successful. Let me go to Vince Wild. Do we have time?
We have time, and we will also take one more question from YouTube after this. We have time. Please go.
We have time. Okay. So this is from Mr. Vince Wild. Thank you for the question. Is there a temperature dependency for viral circulation in a room? The short answer is yes, there is, and we haven't considered that. As I mentioned, we had to do various assumptions. They were not very restrictive, the assumptions, in the sense that we managed to get good agreement with real super spreader events. But when you have big temperature changes in a room, then yes, you have to take that into account. For example, if a room is air conditioned, usually it's maintained at a constant temperature, right? So then that's less of an effect. So for natural ventilation, it will be a more important thing to consider, the temperature variations. I don't see, I have one question left from Mr. Arnab Bhattacharya.
Yeah, and can we take the YouTube question first? It's short, and then we can come back to Arnab's question.
So yeah, okay. So do you want
I will read out the question for you.
Okay, yeah.
So Shailesh Khamari, who is watching on YouTube, asks that since airborne diseases are here since quite long time, is it not surprising that the required models are not well developed? Or is it really well developed and I am unaware?
That's a good question. So I think when the last time there was an airborne disease, which was the influenza, right? We didn't have all the modeling capabilities and simulation capabilities we have now, right? So in some sense, this COVID-19 pandemic came at a time where we had tools to fight it, somebody would say successfully, because we had a lot of scientific tools in our disposal. One of them was very advanced modeling considerations. I mean, all the, for example, I did an MSc in modeling in 2000, and that was one of the like early programs on modeling, right? So you have now people that are very well trained in modeling, and you have seen models playing a very important role during the pandemic. So the airborne transmission, which is a subset of the questions people have been considering, benefited from this very highly advanced knowledge of modeling. And that's why there's an explanation why we didn't have an advanced model, I think, in the beginning of the 20th century. It was simply there wasn't the science to do that at the moment, in a way.
Okay, so we still have a few minutes, so maybe we can take Arnab's second question. So that was, does your model use a size cutoff for which infectious respiratory particles are likely to be transmitted through the air and be capable of entering the human respiratory tract directly via inhalation? And does model have an evaporation rate for larger particles, which is like humidity, ambient temperature, airflow, etc., which makes larger particles smaller, eventually reaching the size cutoff in one?
Yeah, so you do have all these questions fall under taking into account particle effects, as we call them. One of the postdoctoral researchers we had, Raquel Gonzalez Farina, did look into that, the cutoff size for transmission, what happens with the evaporation rate. There were quite well established evaporation curves you get for these particles. So, I mean, just to summarize your question, for this model we have presented today, no, we don't show that, but we have another piece of work where we have incorporated these considerations, and other people have done as well. There's been a lot of work on these different particle sizes, cutoff size for transmission, etc.
Thank you very much, Katrina. And I think I don't see any more questions. So this was really a very interesting talk. And I think we had a lot of lively discussion. In case people, we are unable to take questions due to time, and if there are more questions, you please send an email to the speaker. She's already shared the contact and she will be happy to answer the thing. So definitely. Thank you very much, Katrina. It was really indeed a very, very exciting talk.
Thank you very much, Professor. Bye.
So we now will move on. Yeah, thanks a lot. Yeah. We now move on to the second part of the today's program. And the second lecture will be given by Professor Gautam Menon. Gautam Menon is a professor of physics and biology at Ashoka University and is also the director of its Center for Climate Change and Sustainability, as it's called 3CS. That's an interesting name. He has also like many laurels and many affiliations. So he is a professor right now on Main at Ashoka University. So he originally belonged to this other institute in south of India at the Theoretical Physics and Computational Biology Group in the Institute of Mathematical Science, Chennai. He is also the founding dean of the Computational Biology Group at this IMSC, or Institute of Mathematical Science. He is currently an adjunct professor at Tata Institute of Fundamental Research, Mumbai. So he's my colleague. He's been awarded a prestigious Swarna Jayanti Fellowship of the Department of Science and Technology. He was named as an outstanding research investigator for Department of Atomic Energy and SRC, which was named also. He was also named as outstanding referee of the American Physical Society, outstanding reviewer award for reports on programs in physics, and is a Shastri Fellow of the Shastri Indo-Canadian Institute. So a lot of outstanding achievements for Gautam. He is an elected fellow of National Academy of Sciences, India. Apart from his scientific work, he is interested in making science accessible to the public. A Political named him recently in its worldwide list of 100 most influential academics in government. His work on modeling the COVID-19 virus assisted the Indian government during the pandemic last year, and we are very happy to hear from him today, his story of modeling COVID-19. So Gautam, over to you.
Thank you, Vandana. Let me share my screen. We can get to the talk. Yeah, it's a pleasure, and it's a thank you very much to the IOP and the IPA for this invitation to speak here. And I'm very happy that Katrina explored a very important way of dealing with a respiratory disease such as COVID-19. I'm going to take a slightly different tack. What I want to do is to remind you a little bit about what we know about the coronavirus that causes the disease called COVID-19. I'll tell you what the questions are there, what we know from the biology, from the epidemiology, and how all of that information comes into modeling. So remember that COVID-19 is caused by coronavirus. It's called SARS-CoV-2 is the technical name of the virus. This is a virus that started off in a particular way with a particular sequence. It's an RNA virus. It then mutates because everything, all genetic material mutates. And this gives rise to different variants. Most of these variants are probably less infectious than the original one to start out with, but some of them can be more infectious, can move more easily between people. And these variants then potentially could take over the space that was occupied by an earlier version of the virus. It transmits through a respiratory route, and this is something that Katrina explained very well. The question of aerosol, small droplets that can hang in the air for a long time, and therefore be communicated between people far more easily than the larger droplets which might fall to the ground. And this whole question of what is the size of the droplets that are emitted when you cough or sneeze or sing has occupied the community for a fair amount, but now we're fairly clear about the science that lies behind that. The original host for this virus was bats, and there occurred probably around 2 years ago, 2.5 years ago, a spillover event into human beings where a virus that originally belonged and survived very well in a bat as an original host, then moved to some intermediate host, probably in this picture that you see to the right, the wholesale market at Hunan and in Wuhan. And that's where it moved from bat to animal to human being. And it suddenly discovered that it could survive within a human host. And because humans had no prior immunity to this virus, it was able to propagate very well. The one point to note here is the importance of the ecology of disease. We're not talking about diseases that are peculiar only to humans and only move between humans. This disease happened because there was originally a non-human host for this. And through some process that is still somewhat unclear, the virus changed sufficiently so as to be able to infect a human, which is why these questions must be approached in the broader context of the ecology of disease. This is important because 3 out of every 4 emerging infectious diseases, new diseases, for example, the Nipah virus, are all come to us from animals, typically from bats and then to intermediate animals and then to human beings again. But this is why we need to keep track of the interface between human beings and the environment that surrounds them. What's special about COVID-19 is that because it was not a virus that was natural to human beings, we had no prior immunity. There was nothing that protected Indians or Africans or Russians or Americans any differently from each other. The second interesting thing about COVID-19 is the important role of asymptomatic infections. You can be infected with COVID-19, and typically if you're young, you may show no symptoms of COVID-19 at all, but you may still be capable of infecting someone else. An important number associated with our understanding of COVID-19 is called the infection fatality ratio. And that measures the likelihood of dying from an infection. And this changes or increases very sharply with age. So while you're fairly well protected, the probability of dying from a COVID-19 infection if you're aged between 0 and 19 is really, really small. It's a fraction of a percentage. By the time you get to age 70 and above, this becomes fairly large, about 4 to 5% or more. And therefore, this is something to keep in mind, that COVID-19 really affects the health of people who tend to be older, whereas people who are younger tend to have a fairly mild bout with COVID-19. Of course, these are all generalizations. You may know the 1 or 2 people who were actually young, appeared very fit, and yet had a very bad bout of COVID-19. It's true that these are all statistics. We still don't quite know the factor that made that have one person responding very badly to the disease and another person who shrugs it off without even a second thought. So hospitalization, the severity of the disease, etc., all behave in a similar way as fatalities, and they tend to get worse as you grow older. And of course, pre-existing conditions, typically diabetes or cardiovascular disease, are all important in this regard. Here are the graphs that epidemiologists pore over every day. This is the graph from the beginning of the COVID-19 pandemic, typically starting, you can sort of start it off on the 30th of January of 2020. And you can see the Indian case, where you first saw the gentle peak that we had, this initial peak that around the 15th of September of 2020. and then the very sharp, strong peak associated with the Delta variant that happened between February, March, and about May of 2021. And then the third peak that you can see, which is the Omicron peak, between about January and March of 2022. And on the right-hand side, you can see the analogous death rate. And you can see that the deaths kind of track the cases, except later, by the time you get to the Omicron peak, because given that Omicron seems to be overall somewhat milder compared to the earlier Delta variant, you can see the number of deaths are smaller, and you don't see any further signals in the deaths, even though cases are rising very, very slowly or roughly constant, or have been for the past couple of weeks. And that's because the situation now is very different from the situation that it was earlier. Already, Indians have been exposed to multiple variants of the disease. They've been vaccinated in large numbers. And therefore, the new virus, as it changes, is encountering a population that already has a fair level of prior protection. This is what the map of India looks like with the cases per capita and the deaths per capita. And something will stand out immediately when you look at this. First of all, there's a broad band in the center of India, the states of Uttar Pradesh, Bihar, Madhya Pradesh, Rajasthan, the so-called Bimaru states, where it seems to have fewer cases and fewer deaths per capita. The states where you have a larger number of deaths is the state of Kerala in the south of India, the state of Maharashtra, the state of Karnataka as well, the state of Mizoram on the right-hand side. And these are all examples of the fact that the way the disease appears to strike the country is very inhomogeneous. So that's one thing to remember. And then it's also important to inquire into the reasons for that inhomogeneity. So the impact of COVID-19 has varied across India, indeed it's varied across the world. And one reason for this is differences in demography. The state of Kerala is on average an older state than the other states of India. UP is a young state. And just age alone influences mortality, as we saw in an earlier slide. But there are many other points to keep track of. There are differences in reporting. The quality of public health systems changes from state to state. The measures of mortality change from state to state, as well as prior exposure to different variants, the rates of vaccinations in different levels. All of these can be different. So this is a question that involves space, because you can have spatially different or varying impacts of the epidemic. Time, it depends upon when things have happened. And history, what was the exact sequence of different variants of the SARS-CoV-2 virus that entered the population. And finally, social features. We do know, one thing we do understand about COVID-19 is that it seems to affect disadvantaged populations, the poor, the black populations in the US, far more than it does affluent populations. And so social determinants of the disease are not just for COVID-19, but in a sense for all communicable diseases, very important things to consider. Here's an example of the importance of variants, and this is the fraction of tests that test positive for a particular variant. And you can see that the way the alpha, beta, gamma, delta, omicron of various types have taken over at different rates in different parts of the world. You have Australia, New Zealand, United States, South Africa, and you can see that the structure of these curves is all somewhat different. Which variant went to which country first differs from across these, in fact, across every country in the world. And that's an indication of the fact that we now, when we compare across countries, it's interesting and important to look at the difference in the history in terms of the variants that they actually saw. And how the populations respond now is a function of what happened to them in earlier time. So now let's just get to the modeling. That is a quick survey of what's been happening with COVID-19 very broadly across the world, and the important point that we'll return to when we think about models and the relevance of models. First of all, when we want to understand disease in a population, we must remember that people are heterogeneous. They're not all the same. So you can have a bunch of susceptible people, infectious people, etc. And we've classified them according to with respect to the disease. If you're susceptible to the disease, you're not exposed to the disease, you've already passed that stage. You're not infected to the disease, but can become infected potentially in the future. If you're infectious, you can transmit infection between people. If you're infectious, you can transmit the infection to someone who's susceptible. Okay. If you're recovered from the disease, which means you've had the disease, potentially you're protected against that disease for at least for some time, based on what we know at the moment. So now you have just an S, I, and R that represent each individual in the population with reference to their disease state. So now the next step in these models is to put all of the people who are susceptible into one box, all the people who are infected into another box, and all the people who are recovered in the third box. So these are called compartments in the technical literature, and you label the numbers. You look at the numbers of people in each compartment, and that's the fundamental quantity to model. How many susceptibles are there? How many infected people are there? And how many recovered people are there? And now the question is, how do you write down a mathematical description of how the numbers in each of these compartments, each of these boxes actually changes? And those equations, in a very famous formulation due to two Scottish mathematicians, Kermack and McKendrick, are the equation that you see on the left-hand side. And the graphs that you see on the right-hand side is the graph on the top is the representation of the numbers who are infected if the disease is initially seeded by a small number, a small group of people in the population, initially allowed to infect other people. So the disease must start somewhere. But once you have that starting point, what happens to the disease in the future is what is being investigated here. So you can see that these equations to the left have certain quantities of parameters inside them. One is described by the Greek letter beta, one is described by the Greek letter gamma. And if you change beta and gamma, or more precisely the ratio of beta and gamma, you can look at the curves on the right-hand side of the top figure and see that the numbers of infected changes. The numbers of infected at the peak go down as you decrease the value of as you increase the value of beta in this particular case, and it also moves towards the right. And the numbers of those who are infected changes depending upon beta and gamma in this particular graph. What I want to discuss from the point of view of models today is a bunch of different problems that we've been working in. These are examples of different types of models that have been applied to COVID-19 in India. The first example that I will describe is a compartmental model. It's called InsiSim. Then I will generalize the InsiSim model to make it a little more complex and allow for prior infections, allow for 2 doses of vaccination, and ask how does that change the nature of the spread of the disease. So this would, for example, describe India after the vaccination program started and after the first wave of COVID-19 in India. Then I will describe other questions that we're interested in, a network model for testing, a model for how to reopen schools, or when should schools be reopened in the background of a certain amount of people who've already got the infection. And finally, I will describe something that we've been working on intensively for the past year and a half. This is an Asian-based model called BharatSim. So some resemblance to the models that Katrina spoke about, but I will tell you a little bit about why such models are interesting and fairly diverse in their application. So the InsiSim model for COVID-19 is this complicated model, this complicated set of compartments that you see to the right-hand side. So there are many states in this particular picture. It's not just a simple S, I, and R that we saw earlier. There's a susceptible state, there's an exposed state, and then there are 2 infected states. There's an asymptomatic and a pre-symptomatic infected state. The pre-symptomatic case will then develop infections that will show symptoms later on. Then they can be mild symptoms or they can be severe symptoms, in which case you have to be hospitalized. Whereas people who are asymptomatic can recover and they may not even know that they've had the disease. As I said, the fact that a large fraction of people who will contract COVID-19, typically younger people, will show no symptoms at all of the disease, or mild enough symptoms that they ignore it altogether. There are many things that go into this. First of all, we divide each of these little boxes that you see here by age as well. So there are 9 subdivisions describing ages 0 to 10, 10 to 20, 20 to 30, etc. And we also describe, based on social data, the nature of contacts between people. For example, how likely is it that someone aged 0 to 10 or 10 to 20 will contact someone who's aged 70 to 80. So we put the information about these contacts and these contacts across bands of age into this, because that also influences how disease spreads within a population. We can take this and then apply it to what we know about COVID-19 in India. So this is an exercise that looks at the data, looks at the parameters, examines what is reasonable that one can state about those parameters, and then ask from that what is the information that we can actually glean. So the first piece of information that we can get from the modeling exercise that you can see is about 35% of the population were infected in the first wave of COVID-19. And this is a wave that started around the end of January of 2020 and then went on to the February of 2021, at which point a whole new variant, the Delta variant, entered, and then the story changed completely. We can also look at the fraction of undercounting of cases. So how much did you undercount cases? For every case that you managed to detect or test for, how many cases did you miss? And from here, you can figure out that you missed, out of every 1 case that you detected, you missed about 19 cases. The undercounting was about a factor of 20. And you can also estimate the undercounting of deaths. And there we estimate a number of between 2 and 5. We can now go on to more complicated models. And now you can see that the essential philosophy of working with compartmental models of increasing complexity is just to add more compartments. So you have a broad set of compartments that describes an unvaccinated population, another set of compartments that describes a population that has a single dose of vaccine, and a third set of compartments that describes people who have a double dose of vaccine. And of course, you move from these compartments, you move across these compartments, the first set to the second set, after you have 1 dose of vaccine, and you move from the second to the third after you've had 2 doses of vaccine. And all of these connections describe the ways people can be infected. For example, if you've been vaccinated but then are infected, you can then infect people in another compartment. So all of this can now happen. If you're vaccinated with a single dose or a double dose, you can still die, although the probability of death is much smaller than if you were purely unvaccinated. So you can put the numbers in. There are many rates, there are many numbers that figure in, but all of these have to be fixed based on what we know about the epidemiology, based on what we know about the clinical aspects of the disease. And over here, it's important to use information that is already available, for example, from the experience of previous countries. So South Africa was hit by the Omicron variant early on. We can use South African data to try and fix the numbers in this particular graph, in this particular description that you see to the right-hand side. But the nice thing with models is that you can explore counterfactual. You have some idea of how many people were infected at the end of the first of the Delta wave for example, in parts of India. And we studied the case of one particular state called Andhra Pradesh, which we used as a paradigm to study more broadly what is happening to COVID-19 in India. So one thing you could say is if you started off and you began to open schools with different levels of infection within the population, it's called the seroprevalence, you can ask what might happen in that case. So when schools were reopened, so you could look at the case where the case at the top is what we know to be the correct seroprevalence, so the correct level of prior disease in the population in the top graph. And the second graph is a counterfactual case where only 20% of people had been infected. And the third graph at the bottom is the case where 40% had been infected before schools were reopened. And you can see that the case where the actual numbers of people of 62%, 64% being infected prior to schools being reopened shows that there was very little change in the numbers of infections. Whereas if fewer people had been infected before that, you then began to see this large increase in cases, which was not seen in real life. So there was no rise in cases once schools reopened, even though children had not been vaccinated, precisely because background seroprevalence was high in this particular state. We also looked, you can see the third peak there, that's the relative intensity of Omicron. So that's the Omicron peak that's set in across India somewhere between around the 20th of December, early parts of January. And you can see that we fit that as well. And then you can ask what determined the severity of the Omicron, given that it was already impacting a population which had largely been infected, had been vaccinated, etc. And these are questions that we also looked at, both questions of vaccination and the role of prior immunity. You can now put the heterogeneity back in, and one way of doing this is using network or agent-based models. And here we looked at testing strategies, the reopening of schools again, as well as a far more complicated model called Bharatsam, which I will end with in my description of models. So in the case of network models for testing, we were trying to address the following question. India continues to use two types of COVID-19 tests. One is a high sensitivity test called the RT-PCR test, which you all know about. And the second is a low to intermediate sensitivity test, although these tests have improved in sensitivity since we wrote our paper originally. And these are the RAT tests, or the rapid antigen tests. So now the question that you can ask is, how much should you be testing, given that you are at a particular point in the pandemic? What is the mix of RT-PCR to RAT? Because these are somewhat different tests. The RT-PCR test takes some time to return an answer, typically 24 hours. The RAT test is a rapid test. You can get an answer in 15 minutes, even though it's less accurate. What does this mix depend upon? And if you factor in economics, the fact that these two tests cost different amounts of money, how should the mix change? So what we do here is to set up a model in which you describe homes, workplaces, hospitals, and you imagine people moving between homes and workplaces on a certain schedule, moving between workplaces. If they fall seriously ill, they move to hospital. And the picture that you see to the bottom is a network that describes 20,000 or 30,000 people and how the infection begins. So here you're really modeling a group of people, for example, a distribution of family sizes starting between 2 people in a family to about 6 people in a family or 8 people in a family. So describing a distribution of family sizes, a distribution of workplaces, workplace sizes, and interaction between people in the home and in their workplaces, and describing how diseases spread between them. So that's a picture of disease spread inside them. Once you set up a model like this, you can change many things. You can look at the fraction of the RAT test versus the PCR test. You can change the sensitivity of the RAT test, and you can change the fraction of those infected to start out with. So whether you're starting from a population that has had no prior infection altogether, or a population that has a fairly high amount of prior infection, you can construct a graph like this, and then say, I'm going to change the daily testing rate and ask, what is the number of people who are infected right at the end, which is a measure of how effective I've been in controlling the spread of the disease by quarantining people who I identify as being infected. You can change quarantine procedures, you can change the testing rates, you can look at the effects of what are called non-pharmaceutical interventions, which are basically lockdowns, and then try to extract from these models, try to extract from the data some implications for public policy. So how much should you test? Well, somewhere between 0.2 and 0.5% daily. At that point, India was doing about a half to a third of that particular amount. The optimal mix of RT-PCR to RAT, well, it turns out, interestingly, that even all RAT regimes are okay if you test enough. So even all rapid antigen test methods are fine, provided you're just testing in large enough amount to hold the disease back. What does it depend upon? It depends upon where you are in the epidemic curve, the sensitivity of the test, the amount of testing, etc. And we're able to distinguish each of these impacts of each of these in the model that we actually wrote down and computed with. Schools reopened across Indian states on September 1st, 2021, very largely, not all states. And the question that people had at that time was, will cases rise? What happens to the family members of children who go to school? Should the interventions such as masking and localized lockdowns, restrictions on public transport, should they continue at all? And should different states explore different strategies? This is just a more complicated version where you put in schools, you put in workplaces, you put in homes, and you would have certain rules about what happens to people who are identified as testing positive. And here again, you can ask the same question. What happens to school-going children, the ages between 0 and 18? What happens to people who, when they come back to families, they're infected, and they come back to families and infect people in those families? What happens to them at that point? We can look at these questions and then ask, what is the impact of this on cases in schools and on possibly mortality across different age groups? So we answered this in the following. The question of, will cases rise when schools reopen? We said largely yes, mainly in children who have not been vaccinated, but the possibility of severe illness is really minimal in children. And it's a better idea to look for symptoms and to treat those children specifically rather than continue to close down schools. What happens to family members? We found out that family members were largely protected against infection by vaccination. So there was a much smaller rise there. And we suggested, nevertheless, that a good strategy for public policy would be to vaccinate family members of school-going children. The question of should NPIs continue, should the non-pharmaceutical interventions continue? We said yes, it would cushion the impact of the disease, the spread of the disease, and we described different strategies for relaxation of these, with the non-pharmaceutical intervention. Then finally, the next question of should Indian states explore different strategies? And we said yes, that depended upon the extent of the spread of the disease in each of those states. You needed more granular information that looked at the levels of antibodies against COVID-19 in people in those states. Take that information gathered in a statistical manner to try and understand what policy should apply to that particular state. And similar complexities apply to experience of each country. There are many confounders, as you saw in the spread of variants in the earlier case. Each country saw a different variant at different times. And that determined the course of the disease in that country, as well as the prior history of vaccination. So in order to compare between countries, compare between states, one needed more information to be put into these models. We wrote an article, again, intended for the public, and this comes to this question of where are models useful? And one idea that I have, or one suggestion that I have, they're particularly important in understanding what is good policy and how to frame policy that really is the best. And over here, the question of should schools reopen or not is certainly a very important question of policy here, of health policy, because children, of course, are absolutely crucial and central to any society. And it's important to understand what levels of safety apply when you approach this question of opening schools again. BharatSim is the last of the sequence of models that is. So we started with compartmental models that were, in a sense, the simple workhorse of all possible models that we could write down. We then moved to a little more complicated models, which were network models that describe the interactions of people in groups, family groups, at work groups, coming back and forth between family and work, etc., family work, schools, hospitals, etc. But now what we want to do is to try and look at each individual as being completely distinct and different from each other. And that's to consider each individual as what is called an agent. So imagine that we had some way of taking the population of a mid-sized city, for example, of Pune, somewhere between 3 and 5 million, and identifying each individual from the point of view of their age, their location, where they stayed, where they worked, the people they interacted with, the size of their families, the nature of their workplaces, etc. And imagine that we had the sort of granular information that we needed to describe each of these individuals to the level at which the nature of disease transmission between them could be taken care of. For this, you need what is called a synthetic population. You need synthetic populations at a very large scale. The Bharat-Sim, the word Bharat-Sim, Bharat is of course the old name for India. And Bharat-Sim was intended to describe a population that could potentially stretch to all of India, to about 1.4 billion people. So what goes into Bharat-Sim is a very large synthetic population. You can look at it at even subpopulations of that, but typically we might be looking at a mid-sized city or a large city, the city of Pune or the city of Bombay. And what we want to do is now to describe how the agents interact with each other, the schedule at which they go to work, at which they come back, and to be able to visualize what happens in this case. So you have day 21 of a pandemic, the end of the pandemic, etc. over here. So the combination of synthetic population, simulation tools that describes interaction between these agents and how disease moves between them, and finally a way to visualize the data is all that we're looking for. So right now we can do typically about 50 million agents. Our synthetic population is constructed through a variety of surveys, the census, the NSS, the coordinates for all the villages that are available. And to this, we can add all of the information that we have from the epidemiology, the variants, the non-pharmaceutical intervention, people's behavior, the economic decisions that they make, and so on. So here's one example for about 3 million agents, where you can look at two variants. The second is the more transmissible variant, somewhat like the original Wuhan strain, and then the sort of the takeover of that strain by the Delta variant, for example. And you can look at if the probability of reinfection is 100% or 90% or 70% or 60%. How does this curve change? If a prior infection really protects you against a second variant, then what happens? How does that change the nature of this curve? These are all questions that we can now answer within the framework of models such as this. The Bharat-Sim is defined as a framework. That is, it isn't just a program that you sit and run, but something that you can configure to change it to apply to different types of diseases, not just COVID-19. It's adaptable to different types of situations. It includes intervention, for example, lockdowns that you can have. It counts for mask wearing, it counts for anything, the school closure of school, the shutdown of public transport. All of this can be put in principle into Bharat-Sim. Bharat-Sim it's possible to simulate around 50 million agents within Bharat-Sim, and you can see how in the picture how the color of these changes depending upon the count of infections in that particular region. So this is a picture of the Bombay city and the different wards within Bombay city, and our simulations of how the disease spreads indigenously across those wards. You can also use this for different things. You can study model communities, as we did for school reopening. You can look at mixtures of testing. You can look at vaccination, the effects of vaccination, the differential impact of vaccination. But you can also do more things. You can look at other diseases. You can look at vector-borne diseases, the effects of temperature, humidity, climate change, etc., all within this context of agents whose behavior is influenced by the environment around them. We then finally looked at Omicron in India, and this is the two people at the ISI and the ISC in Bangalore made a repository for different projections across multiple models. These combining the predictions of different models to get some sort of collective prediction. It's called an ensemble approach. So these are ensemble models, and they're often used for weather forecasting, where you have a bunch of different models that predict the weather over the next 24 to 48 hours. And you try to find out, to optimize between them, to find out what might be the best projection that you can get if you combine them together. And usually this is a sort of crowdsourcing or a sharing of different approaches in order to get more insight into a particular number, into a particular projection. Overall, for Omicron, in India, the models were accurate. They got the location of the peak roughly right, Jan 25th to February 10th in India. They predicted that the cities would peak earlier and roughly when they would peak in these particular cases. So here are projections for Karnataka and our own projections for what would happen, the number of cases that were severe versus severe but vaccinated with 1 dose or severe vaccinated with 2 doses. And we know that vaccinations do protect you against the more severe parts of the disease, although they will not protect you against infection. So we can put those into the more complicated model that I described for you, the model with these different sets of compartments, the 1 vaccinated compartment, the 2 vaccinated compartment, etc., and get more and more precise information that enables you to project into the future, to try and ask what might happen. So let me just finish up by summarizing what I've told you. I described a variety of models, and they spanned many different types of models, a simple compartmental model, very much in the philosophy of the original SIR model. I told you where that came from and what the S and the I and the R refer to. But then we discovered that we had to do more complicated models if we wanted to describe the effects of vaccination, a 1-dose vaccine, a 2-dose vaccine, etc. Plus the fact that people had been infected earlier. So if we wanted to introduce a vaccine later, after a certain number of people had been infected, when we wanted to understand the consequences of that, then we needed a model that was certainly more complicated than the simple model that I wrote down earlier. Right at the end, I spoke about agents. We went from simple compartmental models where all we were concerned with were the number of people in each compartment. We went from there to networks. And from networks, we moved to agents. And agents are powerful, they're granular, because they describe each individual separately. And it's possible with agents to describe the social determinants of disease. And that's a very important direction that one must think about in the future. Why do diseases affect different populations differently? Why does tuberculosis, for example, or malaria affect some populations, but not so much? Can we make projections in the future for which are the parts of the population that might be most vulnerable so that they can be addressed early on? There are other approaches that I have not spoken about. There are pure statistical models that don't really care about the epidemiology of the disease. There are machine learning models that just look at data and try and learn from prior data. Some of these have been successful in earlier contexts, but they all have pluses and minuses with them. And often the best thing to do is to look at a combination of models, as I said, an ensemble of models. The usefulness of models is really for short-term projection. One should never trust a model that claims to project things 3 months in advance or 2 months in advance, because things change. People's behavior changes. People's behavior is modified by when they look at at other people's behavior, other people falling ill. You yourself may decide to mask, not to go out so much. And it's the change in behavior that's the hardest to put into these models. So really, we can look at short term, maybe a week, maybe 10 days, but really not much longer than that. Longer term, the questions that the models must contend with are questions of climate change. How is that going to change the whole landscape of how disease spreads? Can we expect more spillover events? And that's a question in ecology. As we cut down trees, as we alter the boundaries between human beings and animals, do we expect more spillover events? Certainly we do. But what are the nature of those events? What can we expect in terms of the ecological behavior of disease and the nature of the disease that might spread? Where is this thing happening? Where can we expect the next disease to come from, disease X, you might call it, to come from? Many of the problems that I described had really to do with policy questions. That is, what is good policy? When should you reopen schools? What's the right mixture of testing? What's the right time to do vaccinations? Who should you vaccinate on priority, etc.? That's because that's where I think models are really most useful. They're less useful, in my opinion, in terms of answering specific questions of will there be 6,000 cases in Bombay tomorrow or 12,000 cases across India, etc. These are much harder to figure. But what you can do is to say, given all of what we know about the disease, what things can we do that might change that course? And to what part can we codify that into specific policy? And because we can precisely explore different counterfactuals, different measures, different ways of intervening in clever ways, so that we can ask if combined interventions might be better than single isolated interventions. The idea of using an ensemble of models is very crucial to what I spoke about. I think that the best way to think about models is not to have your own favorite model that you work with, but instead think across multiple models, combine the information from them, look only in the short term, and then extrapolate from there to say that, look, this seems to be sensible, this is not so sensible, this may work, this may not work. And we should retain that humility when we deal with an extremely complex, multifaceted societal event, really, where both society, disease, ecology of disease, the nature of the clinical aspects of that disease, all of these play into each other. Finally, I hope this what I said in the beginning and the way that played out in the talk that I described will give you a hint of the complexity that is involved in these models. First of all, the many variants that we have seen. How does one put these multiple variants? Where can we say anything about new variants? What might the effect of a new variant be if you have been infected earlier and you've been vaccinated early and you have some sort of hybrid immunity, which is a combination of the immunity that you get from a vaccination together with a prior infection? What changes in that particular case? If you do that, you can see that the variants, the histories of the infection across different states of the country, across different countries, all are important in determining what happens in the future. Finally, space. The usefulness of talking about agents is it's a way of putting in space, just as with networks. You can define homes, workplaces, different parts of the city that might be affected differentially and ask how to target interventions to those particular regions at a particular time. Finally, history, space, time, changes in the disease, all of these are necessary to put into better and better models. And right now, at the end of 2 years of the COVID-19, 2.5 years of the COVID-19 pandemic, we are now in a position to have better and better models. But more importantly, understand what models are useful for. They're useful in the short term. Good models are, ensemble models are, and they're good to decide policy, to try and understand, to weigh different versions of policy. And they have to be critiqued at every stage. You have to have better models. You have to have models criticizing other models, models that can then be combined together to give you a more sharper insight into what might happen with the disease. So a lot of people to thank. I'm not going to name each of them individually. We've been supported by a bunch of organizations, including the Gates Foundation, WHO, Ashoka University, Emphasis, and Institute of Mathematical Sciences. Here is a sort of most of my collaborators, not all of them, but specifically I must single out Devayan Gupta and group at Ashoka University who work on the Bharat program, and a collaborator, Sandeep Krishna, Philip Cherian, Brian Wall, Vaibhav Sinha, and Farina Muzaffar, who looked at these questions of school reopenings, questions of Omicron, etc., in the broader context of more complicated compartmental models and network models, with which we could hope to understand the complexity of COVID-19 in India from a model perspective. So with that, let me thank again the IOP and the IPA for the invitation to speak here. And as I said, models are important. We're now at a stage in the pandemic where ventilation is extremely important as a single most important potential non-pharmaceutical intervention that we could think of. At a time when people tend to be wearing masks less and to be congregating more, we have to explore new and novel ways to deal with the way to cut down the transmission of the disease from person to person. And all of this information has to come together for us to be able to understand how to cope with the disease in the longer term. So let me just stop at this point and thank you again.
Thank you, Gautam, for a very nice talk. I think the points which you made are very important, the predictions on the power of the model and what should ultimately be the use of it. And I think the ensemble of models is really an important concept because the COVID, this one lesson which all of us have learned globally is that we need to pull together all efforts, be it for the predictions as well as for dealing with the disease. Yeah, so I already see some questions in the chat box and I request others to type in their questions. So do you want me to read it or you can see the question?
I can see them on them and I can answer them.
Yeah,
There's a question from Shailendra Dahiwale who says, Kerala and Mumbai were most affected. Both are humid places. What do you think? How much has humidity played a role in spreading this infection? So we don't quite understand the climatic how the spread of infection is controlled by climate. It's often true that many respiratory diseases have an oscillatory component that is related to climate. It related both to climate because in more humid situations, the virus tends to survive longer, but also because in the winter, people tend to congregate more. So there are social factors that enter too. In this particular case, I don't think it's the climate or the humidity that is important. I think what is more important is really the fact that these two states have actually good measuring procedures. The true number of cases, the number of cases that are measured or that are tested for actually is closer to the true number of cases than in some other states. So it's just that these states are doing a better job of tracking down COVID cases than other states. I think this is the main reason, not anything else.
Okay, I have one question while people are still thinking and typing. Let me ask you. So this is about the policy part which you mentioned. But as you said that, okay, I mean, the things like taking a decision like when to reopen the schools and all that, do you really, I mean, what I would like to know is that how much role the academics or the models predictions had in the actual policies in this epidemic?
So I think in the UK, there's one example where they're particularly important in deciding what policy decision to take at what time. In India, the situation is somewhat more confused because it's not very clear how policy advice that comes from models is playing into government. And certainly people who have studied these questions or written about them or spoken about them on TVs and other venues have pushed certain ideas about what, and we have certainly looked at these questions from our point of view, explained the models, made them available so that people know what it is that we're doing, shown what the numbers are in order to make specific projections for what might be happening. I think it's important in India to have a more formal procedure by which multiple modeling input flows into government. I think right now, it isn't clear how that is happening. It's happening at an informal level largely. In a few cases, it's happening at a formal level. But globally, I mean, for example, in terms of policy for the entire country in certain areas, it isn't clear where those models are coming from, what those models are saying. So I often make a point of the fact that transparency is important. You have to know what the model assumptions are, how to be, in fact, even to be able potentially to run the model yourself, to understand where numbers came from or to tweak numbers to understand sensitivity. And that's again something that we have to incorporate in understanding how models play into policy. The only useful models there are models that are open and transparent and publicly available. And we should understand how the specificity of those recommendations, what is being said and why it's being said. That hasn't happened so far, really, in any clear way. I hope it happens in the future.
And one more question, maybe it's more appropriate for tomorrow, but let me ask it anyway here. Now that you have a certain experience in the modeling, you think that if you have, I mean, let's hope that we don't have it, but in case when you say the lessons for the future, in terms of modeling,
Sorry, I'm getting cut off.
Okay, no, what I'm saying is that having what we learned about the modeling part from here, how easily or how it can be extrapolated for any other problem if it does come up at this scale. I mean, we of course hope that it doesn't happen, but.
So I think now we're far more experienced with models than we have been earlier. And I think that's one good thing that COVID-19 has done, good in quotes, in the sense we have really understood how to think about respiratory diseases, the complexity of them, look at really complicated questions in ventilation, for example. How do you construct models that describe classrooms or public spaces and restaurants, so on, in a way that you really understand how airflow works. And the nature of the clinical information that is required to go, my models have lots of parameters in them, but all of them must be fixed from what we know about the disease, typically from some sort of epidemiological measurements or clinical information. For example, how much more likely is it that a 70 to 80-year-old will have more severe symptoms than a 10 to 20-year-old? What's the probability that someone who's between 0 and 10 might die of an infection? All of this information we can actually piece together. So now we know what is that information that we need to collect, how do they fit into models, and how do we improve those models? And we also understand the questions that we must ask of these models right now. The questions now are complicated. Once a certain number of people have been infected by first one variant and then a second variant, if a third variant comes along that is partially protected, that you're partially protected against, let's say 50% from your first infection and 20% from your second infection, what happens to you? So the background in which these models function now is far more complicated than anything that we have dealt with in the past. And that's where I think the quality of models has really improved. And that's where I think that this is the one really profound and important learning that we have from COVID-19, thinking about models in the context of COVID-19.
Okay, there is a question in the chat box, in the question box.
Yeah, that's a question that says, how do you decide which models to combine in an ensemble? Have you compared different models or ensemble models versus single models? That's a great question. And usually one way to do it would be to say that, look, I'm going to look at the projections of a bunch of models over the next week or 10 days. Models that do better, I'm going to weight them a little more. I'm going to give them a little more importance in deciding what I'm going to do in the weeks after that. And I'm going to keep doing this dynamically. Each model will then predict for 1 week ahead. I combine the predictions of these models into a single projection with an error bar on them. But then the mix of these models, 80% of this model, 20% of this model, or 50%, 40%, 10%, etc. That mix is what I decide based on how successful they have been in the past. That way, better models are just understood, they contribute more, but you don't ignore other models which may do better a little later, because the assumptions that they make may be a little more appropriate to the situation at a later point rather than an earlier point. That's the way one should think of models. We should not weight them all equally, but we should be able to dynamically change the weighting that they actually get based on how they have been performing in the past, and keep doing that as you update. So overall, I think that the effort at ensemble modeling, the first one that we did in India, was really the effort of the two people that I mentioned at ISI and ISC. Overall, the combined, since most models agreed about Omicron, this was really done for the Omicron case, the projections of the ensemble and the projections of individual models were fairly similar. It didn't change very much. And our model also did fairly well. So the way to think about ensemble models is that they're a way of crowdsourcing different approaches, putting them together, weighting them based on how they've been performing, and keeping on doing that until you get better and better agreement with what is happening. And that really is the way to go.
Okay, so one more question I have, since anyway I can't type in, I will ask. So what, according to, maybe it's to actually both of you, what do you think was the bottleneck or the real main bottleneck for the models? I mean, what if something was available, we would have been able to make much better prediction on the spread, and that would have helped in sort of reducing the mortality?
Well, that's a great question. I think I'll go first and then maybe Katrina can go second. I mean, certainly in India, I think, and probably throughout many other parts of the world, the question was data and data availability and accuracy of the data. For example, what exactly was the factor by which we were undercounting cases and undercounting deaths? And all of this is important to understand the impact of COVID-19. If you don't count deaths at all, your infection fatality ratio is 0 because there are no deaths at all. So how you count and whether your counting is accurate, it will influence questions of mortality and how mortality figures in those particular models. So certainly data is something where we should do better in the future, have better public health reporting systems, which do a better job of collecting and systematizing data. And of course, the second thing is also clinical information. And I can't sort of blame anyone there because COVID changed very rapidly, multiple variants, complexities, Omicron, Beta, Delta, and the experience of each country was different. And really, it was very, very hard to forecast what might happen in the future with variants. It's just, these are all chance events and random events. And typically, at the point where you start modeling, you don't have information that is how much faster is it spreading than some other variant. You can see that only a little later, but it's much harder to see that in the beginning. So better ways of statistically looking at that, doing this in real time is important. I mean, much of our exercises have been posterior exercises where you go back and say you can explain the past, but really what you want to be able to do is to explain the next week or the next 10 days. We're slowly getting there. We now understand what are the components that are important there. We understand models at many different levels, and all of those different levels are important. But I think policy really using the fact that you can explore many counterfactuals using models is really the important thing that I would stress, which is where these things should be important, not for detailed, so many cases tomorrow, so many cases the day after, etc., but a broad picture of what might be happening. Katrina, do go ahead.
Yeah, I think models played a very important role during the pandemic, and they're bound to continue to play a very important role. There is still some skepticism that is quite problematic sometimes, and it shouldn't be there. Of course, I'm biased because I've been a modeler and for a long time now, and we love our models, etc. As Gautam is smiling as well. But I mean, it has to be clearly communicated, I guess again and again to the policymakers that no model is perfect. Right? You can get insights from different models, as Gautam very nicely explained. You can weigh the models, and you can use the model to shine on a particular aspect of a problem, another model to shine on another aspect, and then together you form some understanding of the situation. And this has happened during the pandemic. In the UK, has been done in a quite organized way, because there was also there was an advisory group that was put together for previous epidemics, and that was activated, and then other people were added that knew a lot about modeling. And in other countries, not so much, but I think there is a great room for putting more modeling and science thinking into policy making.
So you think some, like a certain thing, like as you said, they activated the group from the past. So there should always be like a disaster management. There should be some backup which should be there. Yeah, okay. I guess some of these things will get discussed more in detail tomorrow. So we will definitely look forward to that. I don't see any more questions. Let me just see on YouTube. No, I don't see there, apart from the appreciations of the talk. So then we will bring to this first part to the conclusion today. And thank you, Katrina and Gautam, for again very exciting talks and provided insight into all that has gone into the model. And though it's for most of the physics people, they will know about the models, this was a different aspect. So thank you very much for very illuminating talks and for keeping to the time, so that we have been able to also conduct the program well in time. And thanks to all the participants, both on Zoom and on the YouTube. And a reminder to you that tomorrow we again meet at 5 o'clock Indian Standard Time. And let me get the time right, 12:30 GMT. So that's the time we meet, and we'll have an exciting panel discussion tomorrow on the lessons for the future. So thank you again for joining this IPA IOP Cockroft Walton webinar series. See you tomorrow. Goodbye. Good evening. Have a nice day. Bye-bye.
Bye, everybody.